Hi, welcome back. Now in this lesson, we'll be covering some basic number types and looking at different number sets, so we'll be focusing on our rational numbers and irrational numbers, and also we'll be looking at the real number set and seeing why this set is actually a union of our rational number set and our irrational number set. Now, we'll also be looking at different types of integers, such as your even and odd numbers, prime numbers, composite numbers, and square numbers. Now, let's get right into the lesson, and we'll first start out by discussing what are called positive numbers. Now, a positive number is nothing more than real numbers that are greater than 0, right? And we will soon see what exactly we mean by real numbers. But, for now, pretty much any number that you can actually write on a number line is a real number. And so when we say a positive number, we're really talking about a number that is greater than 0, all right? So to the left of 0, we will have negative numbers. To the right of 0, we will have positive numbers. So as an example, we will have 1, 2, and 3 being positive numbers. And for negative numbers, naturally you would have your negative 5, negative 4, negative 3, negative 2, and negative 1, all right? And this can go on and on and on to negative infinity. Now, because 0 itself has no sign, neither the positive numbers nor the negative numbers include 0, all right? So 0 is not a positive nor a negative number, but, to facilitate 0, we can actually define what we call non-negative numbers, all right? So if a number is non-negative, it only means that this can either be 0 or positive, all right? And if a number is non-positive, then this thing can either be 0 or negative. All right, so some very nice concepts here. Now, in order to understand the different types of number sets, it's very important that we understand our number line and just seeing where things fall on this line. All right, so a real number line, or simply a number line, allows us to visually display real numbers by associating them with unique points on the line. All right, so again, here we have our 0, okay? And this is a very interesting concept, as you will see when we look at number bases. But, for now, 0 is pretty much representing your middle point between your negative infinity and your positive infinity. Now, notice here that we will have, 1, 2, 3, 4, 5, and this thing can go on and on and on, all the way into positive infinity. And, though we're looking at 1, 2, 3, you can actually find intermediate values here. All right? So I can actually find a 0.5 here, a 0.7, and so on. You can almost find any point on this line. Now, similarly, on your negative section of this line, you can find negative values, and you can go from -1 all the way up to negative infinity. All right, and just as we did here, we can actually find a -2.5 and so on. So if you go to your left, you're getting smaller and smaller and smaller, as -10 is actually less than, let's say, a -2. -2 is less than a +1, and so on. All right, so values to your left are always less than values to your right. All right, that's the big idea on this number line here. And similarly, values to your right, such as a 4, are always greater than values to your left. All right, so 4 is greater than 0, and so on. Now, every number on our number line that we just saw can actually be represented based on a few properties. All right, so we will discuss a few of them here. And for starters, we will discuss what we call rational numbers. All right, and the reason we will be focusing on our rational numbers is simply because our real numbers that we looked at on our number line, actually can be broken down into two smaller sets. All right, so we're going to talk about first our rational numbers, and then we will be looking at our irrational numbers, and we will see exactly what these things are all about. Now, as a quick depiction of how this number system is actually set up, we will have a big set that contains our real numbers. All right, so all numbers on your number line are actually real numbers. Now, I can actually break down that real number into two sets, as we saw here, and we will call this set rational numbers, and then we will call this set irrational numbers. Now, I can further break down my rational numbers into what we call integers, which can be broken down into whole numbers, which can be further broken down into natural numbers. Alright, so this is just a quick bit on rational numbers. So let us look at each of these individually and see if we can actually identify some properties of each. So let's start out by looking at our natural numbers, and all these are pretty much positive counting numbers. All right, so natural numbers are 1, 2, 3, 4, 5, just about any number that you can actually count, and we're really looking at positive numbers. All right, so this goes on and on and on into infinity. So this set includes all the counting numbers, as we said here, from 1 to infinity. Now we can use the symbol n to denote our natural number set. Okay, so we would say n equals 1, 2, 3, 4, 5, and we can just use this to show that this set actually goes off into infinity, and we have a nice representation here. Okay, so this is our natural number set. Now what about our whole number set? Now, as an official definition for whole numbers, these are really natural numbers including 0. Now note that not all, well, this says natural numbers, but this should really have been not all whole numbers are natural numbers. All right, so let me just make this quick correction. And we see this because we see that all natural numbers are actually whole numbers, but not all whole numbers are natural numbers. We have a whole number 0 that is actually not a natural number. All right, so that's just a quick take-home message. All right, so not all whole numbers are natural numbers, but all natural numbers, all right, so this is natural numbers, are actually whole numbers. So this set can be written as W, which is equal to 0, 1, 2, 3, all the way up to infinity. All right, so pretty much all counting numbers including 0. Now let's look at our integer set. Well, all this set is pretty much negative and positive counting numbers. All right, so we're really looking at, let's say, negative 5, negative 4, negative 3. This goes all the way to 0, and then you can start at 0 and go to your positive counting numbers, and this goes into infinity. All right, so as a symbol we usually use Z to denote our integers, and by that note you can actually have what we call positive integers. All right, so if we had to define positive integers, then clearly this would be a nice little plus, and this would represent all your numbers 1, 2, 3, all the way up to positive infinity. Now note that our positive integer set is actually the same thing as your natural number set. All right, so that's a quick take-home message there. And there really isn't much to be said about our negative integer set, as that's all it is, or negative integer set. All right, so if we add Z minus, this is really saying, let me just write this thing better. So this is Z, okay, minus, and this is our negative integer set, which is pretty much all your numbers, negative 6, negative 5, negative 4, all the way to negative 1. All right, so your integer set is actually made up of your negative integers plus your positive integers plus 0. All right, remember 0 is neither a positive number nor a negative number. So we've defined our natural numbers, or whole numbers, and our integers, and now we're going to define our bigger set, which is our rational numbers. So let's have a quick look at exactly what these are. Now, a rational number is nothing more than a number that can be expressed as a fraction of an integer or a non-zero integer. All right, now let's see exactly what this definition is saying. All right, it seems a bit complex, but I'm here to actually tell you that it's actually pretty straightforward. All right, so first I'm going to define my symbol. All right, so we will have Q. Okay, so Q represents our rational numbers, and as the definition says, this thing is really any number that can be represented by a fraction, just as we have here, such that your numerator is an integer, meaning some number, let's say a negative 4, 5, it is some number, and b is also some number as well. And importantly, you cannot divide by 0, and so your denominator can never be 0. Right? If you were to put any number divided by 0 into your calculator, you'll actually get what I call a math error. Now, A rational number could be, let's say, negative 5 upon 2, negative 4 upon 2. And notice here that negative 4 upon 2 is the same thing as saying negative 2, alright? Because 2 into 2 one time and 2 into 4 two times, alright? So this is actually negative 2. But the take-home message here is that once you can actually write the number in some fraction, then it is actually a rational number, alright? So here we see again negative 3 upon 2, negative 3 upon 3, which is actually 1, negative 1. We have negative a half, 0 upon 1, and this is important as well because 0 upon 1 is really 0, and so 0 is a rational number. Now, what about this? All right, so we have 0.33, and we have two nice little dots above 33. All right, now what does this mean? Well, all this is saying is that you are repeating your 3 all the way through this decimal. All right, so this thing looks all the way here and it goes on forever. Now, notice that there's actually a pattern here. And there's a school rule in math that once you can identify a pattern in any decimal, then it is actually a rational number. And I actually know that this number is actually 1 upon 3. As if you were to put 1 upon 3 into your calculator, then you'd get 0.333 all the way out to infinity. So if I were to put 1 divided by 3, then I would get 0.33 all the way out. All right, so this is actually a rational number as well. Now, we'll end this list by looking at 3 upon 5, 15 upon 10, which is the same thing as 3 upon 2. Okay, so that's 3, that's 2. And this can go on forever. So the take-home message here is that a rational number is nothing more than a number that can be written as a fraction. All right, so once that number can be written as a fraction, then it is actually rational. Now, is a number, let's say 5 divided by root 2 rational? Well, it is not, all right? The reason is simply because root of 2 is actually not an integer. Remember, you have to divide by an integer, and your numerator must also be an integer. And so if you're dividing by root of 2, which is not an integer, then you'll actually get what we call an irrational number. All right, and we will see exactly what those are. Now, as a point of note, non-recurring decimal numbers are not rational numbers, but exact repeating decimal numbers are actually rational. All right, so again, we use our example of 0.33, and because this thing actually repeats all the way out to infinity, then this thing is rational. But if we had a number, let's say at 0.397628, all sort of numbers going about, then this thing is actually not rational. We can't find any pattern, and therefore we will say that this number is irrational. All right, now secondly, the sum, difference, product, and quotient of two rational numbers is actually another rational number. And we saw in the concept of closure that really what this is saying is that this set is a closed set, since if I were to take any two numbers and sum, subtract, find the product or the quotient, then I would actually get back a rational number. All right, so this thing is a closed set, as we saw in section 1. And here we see that with rational numbers, we can actually operate with powers, but the exponent must be an integer. Now, we haven't done powers as yet, so I'll just leave this one for later. And finally, the root of a rational number is not always another rational number. And we saw this here, because if I were to put root 2 into my calculator, then I would actually get some long number that has no value. All right, well, not that it has no value, but it is actually an irrational number. There's no pattern to the number. It is pretty much just numbers on my calculator. All right, so the square root of a number is not always rational. I mean, this would have been rational if I had, for instance, the square root of 9, which I know is 3, and so you'd actually have 5 divided by 3. So this brings us to our irrational numbers, which is pretty much a set in and of itself. All right, so we're through discussing our rational numbers, and now we're discussing our irrational numbers. And we said that if a number is not rational and it is a real number, then it must be irrational. Now, a number is irrational if there are infinite non-recurrent decimal places. Therefore, it cannot be expressed in the form of a fraction, just as we just saw. then this thing is actually irrational. So once it has infinite non-recurring decimals, then this thing is actually irrational. Now the symbol for an irrational number is usually I. And don't ask me why we use I. These things are actually just created millions of years ago. And, we'll look at some examples to see if we can actually see what an irrational number is. Now, the first one we're going to look at is root 2. And we just saw in our calculator that root 2 has no set pattern to it. All right, it's just a number that goes on and on and on. And this thing is clearly irrational. Now, what about root 2 upon 2? Here's an interesting thought, and I'm just going to pick at your brain a little. This is actually root 2 divided by 2. And if you were to think about it, if I took the square root of 9 to be 3, and let's say I multiplied root 9 times root 9, then this would actually be 3 times 3. And so this would give me about 9. All right, so actually root 9 times root 9 gives you back 9. So therefore, root 2 times root 2 should give me back 2. And so if I were to write 2 as root 2 times root 2, then this thing would actually be 1 divided by root 2. Now, again, if I were to use my calculator, 1 divided by root of 2, then you get a non-recurring decimal. All right, so this thing is actually irrational. And the same can be said for this, as if you had, let's say, 1 plus the square root of 5 divided by 2, which is 1.618033989, and I'm sure this thing goes on forever. All right, so this is actually irrational as well. Now, what about pi, that number that we know and love? Now, in high school, I'm sure your teachers must have told you that pi can be represented as 3.14, or the very fraction that we know and love, 22 divided by 7. Well, this is not quite true. All right, so there's actually not one single person on this earth that knows the value of pi. All right, you have mathematicians that are still trying to figure out the value of pi, but what your teacher has done is pretty much to give you an approximation to pi. All right, so if you were to look at the first, let's say, 10 digits or however many this is, then you'll actually see that this goes on forever. And if you were to round to 2 decimal places, then you'll actually get 3.14. Right, so this can actually be used to represent pi if you go out to 2 decimal places. But it is important that you understand, as a very good student in math, that pi has no defined value. No one has been able to come up with the full value of pi. This thing actually goes on and on and on forever. And pi is pretty much the ratio of your circumference, all right, to your denominator. All right, so if you were to cancel these things out, then you would end up with pi. All right, so any circle, the length around the circle divided by the length across gives you pi, and the value for this thing is actually unknown. All right, so enough about pi. Let's determine if this thing is actually rational or irrational. Well, it must be irrational since we don't have a value of pi. All right, so if I were to actually put pi into my calculator and I press enter, notice that this thing actually goes all the way out. All right, so I have 3.141592654. This thing actually rounds from my 5 to 4, and depending on your calculator, you have some calculators that can actually go out many more digits. All right, so I won't attempt to do that here. Just know that pi is actually irrational, and these are actually approximations. So pi is approximately 3.14 or 22 upon 7. All right, so never write pi is equal to 3.14. This is actually incorrect. Now, what about e? All right, so there's this value on your calculator, we call it e, and it's right here. All right, so it's actually right here. Notice that there's a little e here that you can get from using alpha e, and you get this long value. Again, this is irrational. There's no pattern to this number. Well, I'm seeing 828, but this thing is actually not repeated as you go out. All right, so this is actually irrational as well. So you understand now what are irrational numbers. Numbers that pretty much has no set pattern in terms of the decimal representation of the number, and hence cannot be written as a fraction. So now that we've defined our irrational numbers and also we've defined our rational numbers, then we have pretty much defined our real number set, which is, pretty much bringing together our rational numbers and our irrational numbers. All right, so your rational and irrational numbers will give you your set R, which is your set of all real numbers. So we said that your number line actually consists of all the numbers that you can think about, whether it be a rational number or an irrational number. It is available on your number line. So I've just done a quick diagram for you to see exactly what we've just discussed. And here I have my irrational numbers such as root 2, root 35, and so on. I have my rational numbers, okay, which is pretty much any number that can be written as a fraction. So we see all of these numbers here. And in that, we will have integers that are a subset of your rational numbers. So your integer values are pretty much your values that does not have a decimal point. Okay, so we're talking about stuff like -5, -4, -3, -2, and so on. 0, 1, 2, 3, 4, 5. Now here we have natural numbers being all of this. Well, this is just a simplified version, as we know that natural numbers technically does not include 0. And if you were to include 0, then you would really be looking at your whole number set. Now, I must warn you that there are actually a number of textbooks that represents natural number as having 0. And, don't be alarmed. All they are pretty much doing is a quick shortcut, all right? So they're just jumping a step. You know that the natural number set does not include your 0, but your whole number set includes your 0. Now let's turn our attention to discussing different types of integers. So we will start out by looking at our even number set. And all these things are numbers that can be divided evenly by 2. All right, so once you have a number, let's say 10, that can be divided by 2 without leaving a remainder, then you have what we call an even number. So we say that 10 is even. Now, this actually is a very cool point. Negative values are actually even as well. All right, so -6 divided by 2 is actually -3, and I don't get a remainder, and so -6 must be even. And finally, 0 divided by 2 is actually 0, not leaving a remainder, and so this thing is actually an even number. All right, so just to demystify that point, I know a number of students have asked this question before: is 0 an even number? Well, the answer to that question is yes. All right, so 0 is even. And just about any number that you can divide by 2 without leaving a remainder is also even. All right, so enough with that. Now, what about our odd numbers? Well, odd numbers are really numbers that cannot be evenly divided by 2. All right, so let's take it 3, 1, -3, 7, 11. I could go all day with this thing. Just about any number that you divide by 2 and it leaves a remainder. Now, if you were to add your odd number set to your even number set, then you'd get the set of all integers. All right, so you would get the set of all integers if you were to add these two sets. And here we have just summarized what we've just said by 0 is considered an even number, and even numbers ends in 0, 2, 4, 6, 8. So just about any number that you see ending in either of these digits, then it will be even, while odd numbers end in 1, 3, 5, 7, 9. All right, so this is just a quick bit. So you have a quick shortcut to figure out whether a number is even or not. Now, what about prime numbers? These set of numbers are actually heavily tested on exams, and so it is very important that you understand what is a prime number. Well, this thing turns out to be very straightforward, as all it is pretty much a number that can only be divided by 1 and itself. Now, what do I mean by that? Well, let's look at the number 7. All right, so if I were to divide 7 by 1, I will get 7. And if I divide 7 by 7, I will get 1. Now, no other number can actually divide 7 without leaving a remainder, right? So 5 cannot go into 7, 3 cannot go into 7, and I cannot find any number that can go into 7 apart from 1 and 7, and therefore 7 is a prime number. Now, Why is 2 a prime number given that fact? Well, 2 divided by 2 is actually 1, and 2 divided by 1 is actually 2. Now, there are no other numbers that can actually divide 2 without leaving a remainder, all right? Now, it has been debated for years why they have left out 1 as a prime number, since 1 divided by 1 is actually 1, and trivially speaking, 1 divided by 1 is 1. Well, there's actually an interesting argument behind that, and you can just go online and Google that. But for now, we take it that 1 is not a prime number. Your lowest prime number that you can have is actually 2. Now, 9 is not a prime number for the same reason that 7 is a prime number, as 9 can be divided by a number that is not 1 or itself, which is 3. All right, so 9 divided by 3 is actually 3. Now, so here we have sort of surmised what we've just discussed by saying that 0 and 1 are not considered prime numbers, and except for 0 and 1, a number is either prime or a composite number, and we'll say exactly what we mean by a composite number. Now, a composite number is a number that can be factored into a product of smaller integers. All right, so we said that a prime number is a number that pretty much can be divided by only 1 and itself, and this is in contrast to a composite number. Let's look at, let's say, 9, which can be found by multiplying 2 numbers, let's say 3 and 3, and this gives us 9, and so we say 9 is composite. And the reverse is actually true, and it helps us to see why the number system is made up of composite and prime numbers. And the reason is simply because if I were to multiply 2 numbers to get 9, it should mean that I should be able to divide 9 by either of those numbers to get some other number. All right, so here we see that 9 divided by 3 is actually 3, and so 9 is not prime because 9 can be divided by some other number. And if it is not prime, then it is composite, since it can be divided by some other number. All right, so that's the basic idea. So here we see that 12, okay, is equal to 2 times 6. And this could have been written 3 times 4, and we could have gone 3 times 2 times 2, and so on. You get the idea. And 72 is equal to 2 times 3 times 3 times 4. And so both of these numbers are actually composite numbers. Now, every integer, as we said, greater than 1 is either prime or a composite number. Now, the final number type that we'll be looking at are our square numbers. And all this is pretty much a number that can be written as some integer times another integer. All right, so here we have 9 again, and 9 is the same thing as 3 squared. Okay, just to get my quick calculator here, if you have 3 squared, and we use this to denote square, then you would end up with 9. All right, so 9 is equal to 3 times 3, which can be written as this, as we said, and so we say 9 is a square number. So it's 144, which is 12 times 12, okay, which is 12 squared. And we can actually define many more square numbers. All right, so we could have had 81, which is 9 times 9. We could have had 400, which is 20 times 20, and so on. You get the basic idea. Now, this takes us to the end of this lesson on numbers and number types. And in our next lesson, we'll discuss some of the finer elements relating to numbers. So see you there.